Hey y'all, welcome back to Alakazam Math Made Easy. I just wanted to jump through a really quick, definitely surface level limit content review, but hopefully that'll kind of refer you into the videos that you actually need to study for your upcoming exam, right? So the first topic we went into is the concept of slope, right? That slope equals the rate of change equals m. And the one function that you're always going to come back to find m, whether it's graphically or from, an equation and data given, is this m equals y2 minus y1 over x2 minus x1. Basically, that tells you that the slope describes the y change over the x change. So there's that. So anytime you have a question asking for the slope of whatever line you're looking at, use that m equation, because this equation will tell you the slope. And then anytime it asks you for the equation of that line that you're looking at, use this equation, not the m equation. Use this equation. Oh, okay, yeah. So use m equation and that. Sorry, I forgot I wrote and down there. So yeah, use the m equation because you're gonna need m inside that, but you're also gonna need to use the point slope form of this function to get the actual equation. And remember that when you write equations into like the homework text box, it asks you for y equals some value. So you're going to have to simplify by moving this value over at the very least. So there's that. So if you have a graph, what do we do? Literally, I think the easiest way to do it is just count, right? So you'll be given the blue line on that graph is the original function. The red line is the line you're approximating, and you're given not the 2 points that I established, but the one here at the bottom. You're given this point, and you're given this point at the top. But what they're asking you is for slope. So it doesn't matter what points along the line you use because it's a line. The slope should be the same consistently throughout. So I found that there was a point kind of in the middle that helped me approximate the slope in the smaller amount of numbers, right? So what I'm going to do is I'm going to say I know that m is the y change over the x change, or the rise of the line over the run, right? So what I'm going to do is I know I have to go from this point up to here vertically, right? So I know that that ended up being about 2.5. So that's where this number came from. And then I know that my run, I'm going to have to go across from where I was over to here, and that was 2 boxes. So that's where this 2 came from. So then I simplified that and got 125. So that's my slope. So honestly, it's easiest to count if you're having a graph, or plug in the values of the points you're given up there. And then it's another super important thing to understand, the difference between instantaneous rate of change and average rate of change, right? So instantaneous rate of change is telling you exactly how it's changing at one point, at that specific point in time. So that should be the giveaway, that you're using 1 point on that graph to find that rate of change. The average rate of change is saying, all right, well, I just need to know generally how fast I was going between like here and there, right? So because of that here and there concept of it, that should be the giveaway that you use 2 points. And when we, in a minute, we'll see that 1 point is associated with tangents and 2 points are associated with secant line. So that's kind of a perfect segue into this second general topic, but still in the first video, is exploring the differences between a secant line and a tangent line, right? So again, the original functions are in blue and the lines we're looking at are in red here at this top section. Basically, the biggest difference is built into the definition, right? So a secant line crosses the function at 2 points, and a tangent line only crosses it at 1 point, but you can think of it more, instead of just like crossing it at 1 point, you have to think about it as like you're pushing that tangent line up against the function just so it rests on it at 1 point. So that's the graphical definition of it, right? So if the question tells you to find the equation of the secant line or the equation of the tangent line, for a secant line, the questions will be built differently, right? So because a secant line is inherently used with 2 x values, right? The question will state, find the equation of the secant line of some function between these 2 x values. Whereas a tangent line question will say, find the equation of a tangent line at this 1 x value, right? So we have to kind of adjust the way we're approaching that, because if you remember, anytime we're finding an equation, we need to use this m concept, right? We need to find the slope to find the equation. So for the secant line, that's pretty easy because we're given 2 points. So we're given the 2 x values. We're given the values in the denominator of this m equation. So this we have, and this we have. We're also given the function, right? So I can plug in x2 into that function and get y2. I can same plug in x1 to get y1. So now I have m. So m is here. And then I just use my first value of x and the corresponding value of y. So now I have my entire value, my entire function of y. So what happens to this concept of this m equation if I'm only given 1 point, right? So remember, in this m equation, I had both x values. For a tangent line, you're only given the 1 x value. So the issue is, or not the issue, but the workaround is, you're going to end up having to essentially arbitrarily choose a second x value, because that's what the equation requires. But the difference is, we're going to choose an x value that's incredibly close to the one that we were given. So for example, for a secant line, the values could be 1 and 3, for example, x equals 1 and x equals 3. For a tangent line, it would look more like x equals 1 and 1.01. So that's a much, much, much tighter window that we're looking at. So now we have, so for example, our x equals 1 and our x equals 1.01. And then we would plug 1 in to get whatever that function value is, and then same thing, plug in that. So now we have m, and plug that in, and you can use the value you were given. A lot of times that'll be a whole number, so easier to plug in and distribute, or you can use the other x value, it doesn't matter. So again, we kind of already gone over this, but find the slope of the secant line between these 2 x values, or find the slope of the tangent line at this x value. It's very similar. You actually had to do it in this past instructions, but basically, because it's only asking for the slope, not the equation, you do the same exact steps, but only plugging into m. You don't have to plug into that second function. But again, for secant, you're given both the x's, you can find both the y's. But what you also, for the tangent, you still have to choose that second x value. And again, keep it super, super close. So this next topic is basically introducing you to a limit, right? So there was 2 approaches we took to describing it. We approached it from a graphical standpoint, and we approached it from more of a numerical standpoint. So from a graphical standpoint, you're evaluating the graph based on how the limit is asking you to. So here I broke down what this limit example says, right? So that literally tells me that I'm walking along the f of x function, approaching a on the x-axis from the left side. So if you remember, if it was to say x approaches a from like plus, that would be from the right side. So this plus or minus tells you which direction to approach the value of a from. And you'll find in the example video, I believe it was video number 2, you'll see why that distinction is important sometimes, because a lot of times they won't match up. And then for numerically, the simplest answer is to plug the value of a into the function, right? And then see what the function does. There's 4 primary outputs of that, right? So either you can get some number over 0, which would tell you that that limit equals infinity, or you can get 0 over some number, which means that limit equals 0, or you could get a number over itself, which tells you that the function equals 1, or you could get 0 over 0, in which case it's kind of a gray area, but we'll get into that in a second. First, I just wanted to jump over these limit laws. I wrote them a little differently here than I did in my video, in video 3. So basically what I'm telling you is all of the functions are the same, all of the laws are the same, but instead of relating it to m and n, at the beginning of that video, I wrote something like this. I said limit as x approaches a, f of x equals m, and limit as x approaches a, g of x equals n. So basically in that video, all of these, like this would be m, and this would be n. And same thing, m, n, and so forth. Just remember that f of x went to m and g of x went to n. So for example, in the ones down here, this would just be k times m. And then same thing, this would be m squared, and this would be square root of m. So I think sometimes it's a little bit easier to look at it two different ways, which is why I wrote it in this review this way. So I think it kind of shows you that essentially what you're saying is that this limit function itself can almost distribute through whatever combination of functions you're looking at. So that kind of allows us to do what we're doing here, right? So again, coming back to that 0 over 0 issue you might run into, that's complicated because you don't know if you look at the rest of these rules, there's similarities between these, right? So this looks like rule 3 in the sense that it's a number over itself. So should it be 1? But also it's 0 over some number. So should it be 0? Or it's a number over 0. So should it be infinity? So it's in a very gray area in terms of what that actually means, what that form actually means. So basically what's happening is, because there's something in your function that you're evaluating that is leading to some 0 over 0, that means that there's a component built into that function that's multiplying through both the numerator and the denominator and causing both of those to be 0. So the logical way to approach that would be to try to find what that value is that's causing your problem and eliminating it. And if you think about it, you're evaluating the limit as x approaches a. So how do I get a to cancel itself, right? If I'm plugging a in for x, I just have to figure out where there's an x minus a inside of those functions. So what you would do is, in a case like this, where generally it's one function over another, right? I would factor x of a out, or x minus a out of both of those functions, and then it would cancel, and then that would also simultaneously cancel my 0 over 0. So you'll be left with some value, some valid number. It'll either be a number, it'll be infinity, or it'll be 0, but it won't be 0 over 0 anymore. So there's that. Jumping into trigonometric limits, or limits of trigonometric functions, the first two are literally just plug and chug. It's saying if I'm looking at the limit as x approaches c, I just plug in c for x and I get sine of c. Same thing here, I plug in c for x and I get cosine c. These two are the ones that you really have to memorize. And I would say to memorize them mostly because I personally hate memorizing math. I feel like math is something that you should not memorize. You should in fact internalize and understand, because if you don't actually understand it, you won't be able to apply it. And a lot of exam questions are applications, not regurgitation. So these I would truly say to memorize, because if you don't remember what they equal, there's no point in remembering that they exist, right? So knowing them is only half the battle. You'll be able to, so the questions on an exam will most likely be some combination of a couple of these rules. And an example of that was found in video 5. So if you're interested in kind of what I mean by that, basically they'll give you some really big, ugly looking function. And what you'll do is you'll factor out a combination of these rules. And that'll allow you to say, even though the function looks disgusting, I can say, well, I know that this limit equals 1. I know that this limit equals cosine of c, and I know that the other one equals 1. So because of, because of this rule, we can break up an ugly looking function into its components and take the limits of each of those individual components. So that's essentially what this entire topic is about, except they're now throwing in these conditional, like strange looking rules. So another thing that we clarified in this topic is the limit at versus limit of infinity. And if you remember, a limit of infinity was also written as an infinite limit. But I think it's easier to remember at versus of, right? Because it's a limit of infinity tells you that that final value is infinity. The limit at infinity tells you that to find the limit, I'm looking at x equals infinity. So that's basically how I remember it, how I separate the two in my head, because the language is super confusing. because of its similarities, right? So a limit of infinity tells you that the final value will be infinity, and a limit at infinity tells you that that a value, or as x approaches a will be infinity. So that's how you tell from like a numerical standpoint. Like if you're given the equation, that's how you tell. But what happens if I'm given the graph, right? If the limit of the function is infinity, that means that the function is rapidly increasing as it approaches whatever I'm looking at, the x value I'm looking at. And the flip side of that coin is that if the limit at x equals infinity is some number, that means that it's getting infinitely closer to that number as the function grows. So what does that mean? That means that for a limit of infinity, or an infinite limit, that there's going to inherently be some vertical asymptote at x equals a, at wherever you're looking. And then so for the horizontal asymptote, that'll tell you that there's a limit at infinity, because your function is getting closer and closer and closer and closer to that point. So yeah, that's the horizontal asymptote. So there's some tricks to identify it when it's written as a function, and there's some tricks to identify it when it's drawn as a graph. Okay, intermediate value theorem, I get way too excited about because of what it actually means in real life, right? So intermediate value theorem basically says if I have a continuous function, right? So if I can draw the function without picking up my pen, which is exhibited in this drawing, right? I can draw that without picking up my pen. And if I'm looking in a small section between A and B, right? So here's my A, here's my B, I will have a point where that function crosses some arbitrary number W, as long as W is between f of A and f of B, right? Which logically should make sense. I have to cross through every number between f of A and f of B if the function is continuous in that range, right? So I can't pick up my pen and skip a number. So I would have to cross every number. So that's basically why it's saying any W between those points, a limit will exist there. So the other application, or the other little asterisk in that, is that it doesn't say that there is one W that will be true. It says there's at least one W. So that helps us to like consider these functions that are all kinds of swoopy and wavy, because there's multiple points on this middle function where we cross that W value, right? And then this last part, this third function all the way on the right, shows us that if the value starts, if f of A is less than 0 and f of B is greater than 0, or the other way around, we can call W the x-axis, and that would mean that the function crosses the x-axis at that point, which, if you remember from algebra, was a lot of what we ended up doing, right? We were looking for where the function crosses the x-axis, and we can approximate that on super ugly functions using the intermediate value theorem. And here's an example of how we did that. Basically, we work through it. We're given a function. Is there a 0 between these two x values? So all you do is you plug in those x values into the function and figure out where the f of A and f of B are. And because it's asking for a 0, you need one of those to be greater than 0 and one of those to be less than 0. And because that's satisfied here, yes, there will be a 0. But I go into in the video how we can approximate a little bit, like a tighter window of where that 0 would be, right? And that just involves plugging and chugging new x values into these into the function to figure out exactly where it switches from negative to positive, because where it switches from negative to positive or positive to negative is where there's a 0, right? So that's that I explore that a little bit more in the video. I believe it is video 7. Yep. So there's that. But this topic seems super vague and not really important. But again, I go into in the video how this has applications for some serious real life uses, right? Because not all functions, actually very few functions in real life are beautiful, like y equals x squared. That rarely exists in real life. So if you have something that's disgusting, like a combination of exponentials, trig, polynomials, you can still approximate where a 0 is given that window and testing the corresponding y values. So there's that. And then the last topic we went over is formal definition of a limit. I would recommend watching that video to go over the actual explanation of the logic behind this. But technically, all this process involves is a lot of people get scared because they see these values they've never seen before. This is the first time they've introduced these characters in Calc 1, right? So a lot of times that's the intimidating part. But really all you're doing is playing around with information you're given to make everything equal each other in some way, right? So start with manipulating, first of all, plug in all of the values in your limit, right? So plug in L in this function, plug in A in, where the heck is A? Oh, this is supposed to be X minus A, my bad. Yeah, so plug in A in that function, and then f of X over here, and then simplify everything, and then we can start, right? But when you simplify everything, you're going to start by looking at this function here, right? You're going to start by considering this one, and you're going to try to simplify this piece to just get absolute value of X. So once you get absolute value of X is less than whatever you needed to do to epsilon to make that happen, you're going to set whatever that epsilon combination is equal to this delta value over here. And we can do that because essentially that form, and once you move this A value over to here, this form will be equal, right? So that's why we can do that. And then what you're going to do is you're going to use this new delta equals some version of whatever epsilon combination you've got. And you're going to try to plug that in and get back to this f of X minus L is less than epsilon. So my recommendation would be I go through an example in video 8. A lot of times that's a definitely more intimidating concept for people because of the fact that they have these new characters and then the question says prove that. A lot of people kind of immediately get a little bit thrown off by the actual formality of it. But the math behind, like the process behind it is pretty much the same every time. And the math behind it is fairly, I don't want to say simple, but fairly straightforward. So if you learned something from this video, please like it. If you need to refer back to another video to go over topics a little bit more intimately, I think I said which video corresponds to each topic through here, but basically it's videos 1 through 8 in this same playlist. If you want to stay updated when I upload new videos, please subscribe to my channel and hit the little bell button to get notifications for when I do. And as always, best of luck.